Hello everyone. What we did in the last video is we learned about this new type of coordinate system called called polar coordinates. What we want to do in this video is we don't want to just look at how to convert points from polar to rectangular coordinates, but how would equations look in different coordinate systems? Most of your entire math career, or probably your entire math career, you've only been looking at equations in rectangular form. What would those equations look like in polar form? Or how could we convert between the two different forms? And that's what we're going to do here. So this is the picture you should always have in your head whenever you're working with polar equations. So the key things that we're going to need in this video is just knowing how to go from polar to rectangular. What tools do we have in our belt? Well, we should know that x is equivalent to r cosine of theta, y is equivalent to r sine of theta. And if we are given something in rectangular form, or rectangular coordinates, how can I relate those to polar coordinates? Well, we have the Pythagorean theorem. And we also have that the tangent of this angle will always be y over x. So these are the tools that we have when trying to convert from one coordinate system to the other. Okay, let's just do some examples. So what's actually really great about working in polar coordinates is whenever you are dealing with something that is kind of circular, it's a lot more natural to work in polar coordinates rather than working in rectangular coordinates. The further you kind of go into calculus, sometimes you try to tackle a problem in rectangular coordinates because that's how we're used to working in rectangular coordinates, and you'll find that you really have to work really hard and you really have to brute force it. But actually just switching into a coordinate system that's more natural for working with circles can make the problem a cinch. Okay, so let's say, for example, let's say we have this equation which will be in rectangular coordinates. Let's say x squared plus y squared is equal to 9. So you might already know what this equation is or what this is describing, but if you don't, I'm going to kind of hold off. This has x's and y's in it, so we are in rectangular coordinates. But we would like to transform this to have r's and thetas in it. So what we can do here is we can remember, let's get a different color, is that x is equivalent to r times the cosine of theta, and y is equivalent to r times the sine of theta. So if we make these substitutions, okay, so I'll put a r cosine of theta here, and that's being squared, plus we'll have our r sine of theta for y, that's being squared. This is all being equal to 9. Okay. Well, when we square this, we're going to get out a r squared times a cosine squared, since exponents distribute through multiplication, plus we'll get an r squared times sine squared of theta, and that'll all still be equal to 9. Okay, let's go ahead and clean this up a little bit. Let's notice that we can factor out an r squared, or both these terms have a common factor of r squared, so we can factor that out. So r squared times the cosine squared of theta plus the sine squared of theta, well, that's all going to be equal to 9. But cosine squared plus sine squared, that's just equal to 1. So this just comes down to r being equal to, or r squared being equal to 9. We could square root both sides, and we could say that r could be equal to the plus or minus square root of 9, or we have that r could be equal to 3, or we have that r could be equal to negative 3. So we have two different versions here. That's saying that the equation x squared plus y squared being equal to 9 can be represented in two different ways in polar coordinates. Now this shouldn't be surprising, because in the last video we learned that polar coordinates oftentimes, or polar coordinates, at least for points, don't have unique representations. So here I'm claiming that x squared plus y squared equaling 9 is equivalent in polar coordinates to r being 3 or r being negative 3. Notice that these are independent of theta. Say independent of theta. So really what this is saying, if we're drawing this, okay, I'm going to draw this picture here. If we're looking at the equation r equals 3, well, what this is saying, if we're going to graph this, this is saying regardless of whatever the angle is, how far you have to go out will always be 3. So you'll be out 3, and regardless of the angle, you'll always have a radius of 3. So this will be 3, this would be negative 3, and this would be negative 3. So no matter where we are, independent of theta, r is always equal to 3. So this is describing a circle of radius 3. Okay, and hopefully you've seen x squared plus y squared being equal to 9 and recognize that was a circle. But notice how simple its equation is in polar coordinates. Now again, this would be also equivalent if r was being equal to negative 3. Okay, just remember what a negative radius means. That just means if we were to rotate a certain angle theta, that means we would be going in the other direction. So this would be r being equal to negative 3. But it's saying, doesn't matter what theta is, the radius would always be negative 3. So we're still going to get this circle of radius 3. So pretty cool. So x squared plus y squared equaling 9, an equation in polar or in rectangular coordinates, has a very simple representation in polar coordinates. Cool. Okay, let's do some more. We're just going to kind of play around. Okay, as the next example, let's say we have the equation, how about x plus y equals 0? This is in rectangular coordinates. Okay, let's try to think about what this equation would look like. In polar coordinates. I guess maybe it'd be nice to think about what the shape is really describing. I guess in rectangular coordinates, we could rewrite this a little bit differently. If we solve for x, or if we solve for y, y would be equal to negative x. I hope you know that this is a line. Okay, it has a y-intercept of 0, and it has a slope of negative 1. So this is the equation, y equals negative x. Okay, well, what would this line look like in polar coordinates? Okay, well, let's play around. Well, we could replace x with r times the cosine of theta, and we can replace y with r times the sine of theta. This will all be equal to 0. Okay, so I made these substitutions here. Okay, well, let's try to think about what to do from here. Well, I guess we could think here for a second that what if we moved things to one side? What if we wrote this as, how about r times the sine of theta, or how about we factor out the r? So we could have r, we could get the cosine of theta plus the sine of theta. Okay, this could all be equal to 0. So this is saying a few different things. Well, this is saying that r could be equal to 0, or this is saying that cosine of theta plus the sine of theta could be equal to 0 here. So by saying r being equal to 0, this is independent of theta, this is really just describing a single point. And hopefully you see that this single point is on this line. This is just the single point x is equal to 0 and y is equal to 0. Okay, well, what is this here saying? Well, let's go ahead and, I don't know, how about we write this as the cosine of theta is equal to the negative sine of theta. And how about we divide both sides by cosine of theta? Okay, so this would be saying that 1 would be equal to the negative, well, sine of theta over cosine of theta. Sine of theta over cosine of theta, I hope you believe that's tangent of theta. Or this is when tan of theta is equal to negative 1. When tan of theta is equal to negative 1. Okay, well, in this case, let's think about it. What angles would work here? What would be the solution for theta? Well, there's an infinite number of them. Theta could be equal to, I think, how about if you were to do tan inverse of both sides, I think this will spit out negative pi over 4. Okay, but this isn't the only one. This could also be, theta could be equal to, I think, 3 pi over 4. Okay, and you could just add multiples of pi to these. Okay, but let's just focus on this one. This is one representation for this equation in rectangular coordinates into polar coordinates. This is saying that regardless of the radius, so this is, notice this is independent. This is independent of the radius here, independent of the radius. It's saying wherever the radius is, the angle will always be negative pi over 4. Now, that should make sense if we look back at this picture over here, because what is this angle right here? Well, this angle right here, theta, is negative pi over 4. This is saying keep this angle at negative pi over 4 and let the radius vary. So the radius, if it was positive, would be going this way, and if the radius was negative, it would be going this way. So this is indeed describing a line. Now, you could describe this same line by saying that theta is also 3 pi over 4. So, equivalently, if you say that theta is equal to 3 pi over 4, still independent of the radius, this is still describing this same exact line here. So the equation y equals negative x, or how x plus y equals 0, in polar coordinates would be equivalent to just saying that theta is equal to negative pi over 4, or equivalently you could say theta is 3 pi over 4, or any, you could add any multiple of pi to these, and you'd have another equivalent representation. Pretty cool. Okay, let's do something different. I'm gonna erase what we have here. Okay. Let's do an example of some conic sections. So, I don't know, hopefully you remember a little bit of your conic sections from, I guess, pre-calculus 1. That's math 141 at Whatcom. But let's say we want to look at, how about y squared equaling 16x. Okay, if you aren't super familiar with your conics, well, I hope you believe that this is a parabola. Okay, so general equation, this would be a sideways parabola, would be 4px. This is how you write it in conics. So here, this is the same thing as 4 times 4x y squared. So here, the p would be 4. If you don't recall a lot of this conic stuff, it's not going to be a big deal. Just trying to remind you a little bit about conics if you have seen them before, which I hope you have. Okay, this is saying if p is equal to 4, this gives you directions on how to get to your focus and your directrix. So since it's a sideways parabola, y is being squared, we're going to go to the right 4 units. Okay, so here's our focus, and then we would go left 4 units. Okay, this would be our directrix. And the parabola is going to look something like this. Okay, so what a parabola is, if you kind of forget its geometric definition, is any point on a parabola This is a point on the parabola. If you were to find the distance from a point on the parabola to its focus, it would be equivalent. It would be equivalent to the distance from the parabola to the directrix. These would be the same, and that would be the same for any point on the parabola. Okay, I didn't draw this to scale, but these distances here would also be the same. They'd be true anywhere on the parabola. Okay, so actually you could think here, we could think about what let's erase this blue one right here. We could think about if we were to go straight out to the curve and then go this way. Okay, we could actually think about what this distance here would have to be. Well, the definition of a parabola says that this distance will be the same as this distance. Okay, well, what's this physical distance? Well, from here to here is 4, and from here to here is 4, so this distance right here must be 8. 4 plus 4, this must be 8. So this would be the coordinate y equals 8, and if we were to go down here, this would be the coordinate -8. Okay. And if you are pretty rusty on your conics, or if you've never seen conics before, don't worry too much. So all we're going to do here is let's just go ahead and convert. Let's convert this sideways parabola into polar coordinates just to see what it would look like. This is called the focus, and this is the directrix. Okay, so what we're going to do here is just we're going to place our y's with our sine of theta and our x's with our cosine of theta. So making those substitutions, here we're going to have a r sine of theta is going to be equal to a 16 times an r cosine of theta. Okay, let's see what we get here. Okay, looks like we're going to get an r squared sine squared of theta is going to be equal to 16r times the cosine of theta. Okay, so let's see what to do with this. Let's try to clean everything up. I'm going to go ahead and move everything to one side. So how about we write this as r squared times sine squared of theta minus a 16r times the cosine of theta will be equal to 0. Okay, we could go ahead and factor the r out. So we'll be left with an r times a sine squared of theta minus a 16 cosine of theta will be equal to 0. I'm just trying to simplify this as much as possible. Okay, well, what this is saying here is it's saying that either r could be equal to 0, which is just describing a single point on this curve. That's just describing the origin. So r is 0, the radius is 0 for any theta. That's just what this is saying. But what also would be true is that r times sine squared of theta minus 16 cosine of theta would also be equal to 0. That's what we're getting from this piece. Okay, let's go ahead and solve for r here just to, make it look kind of nice. So here we're going to have r times the sine squared of theta will be equal to 16 times the cosine of theta. So whenever you're solving for something in polar coordinates, if you can, it's going to be nice to have r being equal to something or theta being equal to something if you can get it in that form. And I think we can by dividing both sides by sine squared. So here we'll have that r will be equal to, this is going to be 16 times the cosine of theta all over the sine squared of theta, which is a completely fine form to put it in. I would say 100% credit here, but we could clean this up and write it a little bit differently if we'd like. This is the same thing as how about we move it? How about we move this? We move it up here. here, we could equivalently write this as how about r is equal to 16 times the cosine of theta. How about we write this as a sine of theta times an extra sine of theta. That's what sine squared means. So how about we write this 16, instead of being in the numerator, we can move it out front as a cosine over sine times a 16 over 1. Or I can just move the 16 out front. And how about I write this as, I don't know, you could think of a times 1 here. I don't know, how would I put a 16 over 1 if you want to put a 1 there? 16 over 1 times cosine of theta. I'm just trying to show a lot of detail. Sine of theta times a 1 over the sine of theta. So I'm just kind of breaking up this fraction multiplication just to maybe possibly write it in a different form. So cosine over sine, that's the same thing as cotangent of theta, and 1 over sine is the same thing as cosecant of theta. So this is just an equivalent way to write this sideways parabola. Which of these versions looks better to you? I don't know. That's up to the that's up to the person doing the problem here. I don't know. I would say maybe this one just looks a little bit nicer to my eyes, maybe. But these would be an equivalent representation for this parabola, this sideways parabola. I've just now written it in polar coordinates. Cool. So I don't know. It's kind of up to you. Do you think which do you think looks better? Is it look nicer in rectangular coordinates? Does it look nicer in polar coordinates? Well, I don't know. I would say it probably looks a little bit nicer in rectangular coordinates. But this is what it would look like in polar coordinates. That's just my opinion. Okay, let's do another one. Do a couple more. Okay, let's say we have x squared minus y squared is equal to 1. Now you don't have to know what this shape is to convert it into polar coordinates, but if you are familiar with your conics, if maybe you hopefully know what shape this is describing a hyperbola. So again, you don't have to know this. I think it's just good for your math soul to know it. This is the general equation of a hyperbola, one that's at least kind of pointing outward. Would be x squared over a squared plus y squared over b squared is equal to 1, not plus or minus. If it was a plus, it would actually be an ellipse. It's a minus, it's a hyperbola. So for this one, both the a and b would be 1, and that tells you kind of about this central box, which describes the asymptotes of these hyperbola. So hyperbola have asymptotes. So we have this 1 by 1 box, and the asymptotes for hyperbola go through the corners of these boxes. Okay, and the hyperbola will look like this. It's kind of these two kind of outward looking parabola. These aren't the exact shape of a parabola, but they kind of look like two parabolas facing outward. This is what we call almost the unit hyperbola. Okay, well that's just the graph, but let's just convert it in. Let's see what this graph would look like in polar coordinates. Maybe go ahead and pause the video and give this one a shot on your own. Okay, let's do it. We're simply just going to replace our x's with our cosine of theta and our y's with our sine of theta. Okay, let's see what we get. Okay, we can square everything. So this will be r squared times cosine squared of theta minus an r squared times a sine squared of theta, and this will all be equal to 1. Okay. A good thing to notice for this example is we can factor out an r squared. So if we factor out the r squared, we'll be left with a cosine squared of theta minus a sine squared of theta being equal to 1. Okay, this is a little bit different. This isn't a cosine squared plus sine squared. If this was a plus, you'd replace this with a 1. But it's not a plus. But this is also another trig identity that we learned, I think, in chapter 7. This is the double angle formula for cosine. This is r squared times, you write it right here, this is equivalent to the cosine of 2 theta. So cosine is one of the 3 forms of it. Cosine of 2 theta is equal to 1. Okay, so if you want, we could solve for r. I'm just going to leave it in terms of r squared. So we could say that this is r squared. And how about we do a 1 over the cosine of 2 theta? I'm just dividing both sides by cosine of 2 theta. So we could say that this is r squared is equal to, what would this be? This is the same thing as the secant of 2 theta. I guess you could square root both sides and do plus or minus, but I'm just going to leave it in this form here. So this is this r squared equaling a secant of 2 theta. What is this describing in polar coordinates? That's describing x squared minus y squared equals 1, or it's describing this unit hyperbola. Cool. Fun. Okay, let's do another one. We'll go ahead and erase this here. Okay. How about let's think about the line, or let's think about the equation x equals 5. Just simply x equals 5. Okay, so this is a 1, 2, 3, 4, 5. So this says regardless of what the y coordinate is, the x coordinate is always 5. So maybe I'll write that in blue. So this is the equation x equals 5. Doesn't matter what the y value is, the x coordinate's always 5. Okay, let's go ahead and write this in polar coordinates. Okay, if you'd like, you can pause the video and give it a shot on your own. Okay, so this would just be simply writing x is the same thing as r cosine of theta will be equal to 5. We could divide both sides by cosine, so r would be equal to 5 over the cosine of theta. Or we could say this is equivalent to r is equal to 5 times the secant of theta. So interesting enough, x equals 5, this kind of simple equation in rectangular coordinates, I would say has something that's not quite as friendly in polar coordinates, but r being equal to 5 times the secant of theta, this is describing the line x equals 5. Cool. Okay, let's go now in the other direction. Let's say we have something in polar coordinates, and then let's turn it into something that's in rectangular coordinates. I'm going to go ahead and erase what I have here. Let's say that we have the polar equation r equals 2 times the cosecant of theta. And we want to convert this from polar coordinates to rectangular coordinates. So what we want to make happen is we want to try to force this equation to have these types of pieces here. And let's think about a way we can do this. Well, one nice thing we might want to try to do is write everything in terms of sines and cosines. That's always something that can be helpful. So this is the same thing as r is going to be equal to, this will be the same thing as 2 over the sine of theta. Okay. Let's multiply both sides by the sine of theta. And what's great about doing this is we're going to get that r sine of theta piece to show up. So we'll get r times the sine of theta is going to be equivalent, these will cancel out, will just be equivalent to 2. Well, r times the sine of theta is the same thing as y, so we just get out that y is equal to 2. So this is the equation describing a horizontal line. This is saying no matter what the x value is, the y value is always 2. So this is the equation y equals 2. This is its representation in terms of rectangular coordinates. This would be its representation in terms of polar coordinates. Pretty cool. Okay, let's do another example. Let's go ahead and try this next example. Try to convert the equation r equals -4 from polar coordinates to rectangular coordinates. Okay, let's do it. For this one, we'd really just like to get an r squared to show up. In this case, I'm probably not going to want to multiply both sides by r, because then it would be nice for me to have an r squared on the left-hand side, but having a -4r on the right-hand side really isn't going to help us too much. So in this situation, what might be nice for us to do is to actually square both sides. So we'll have that r squared is equal to 16, but r squared is equivalent to x squared plus y squared, which will be equal to 16. And now I hope from here that we recognize that this is a circle of radius 4. And there we have it. Beautiful. Okay, let's do another one. What if we just have, let's say, theta is equal to pi over 3. Go ahead and pause the video and see if you can convert this equation, which is in polar coordinates, into rectangular coordinates. Okay, let's do it. We've actually seen something like this similar in the beginning of the video. If we were thinking about what this is saying is that the angle is always pi over 3. So the angle is always pi over 3, and the radius can be whatever it wants. So I hope you believe the radius is positive, we'd be going out this way. If the radius is negative, we'll be going this way. So this is just the equation of a line. Okay, I guess if you want to, you could, you think about y equals mx plus b. Hopefully you can see the y-intercept is 0, so the b will be 0. Or the y-intercept is at the point 0, 0, so the b will be 0. Also, you could try to do some measurements to figure out the slope here if you wanted to, but that's no fun. We want to try to use our tools here. And the tool here that's screaming at me to use here is that tan of theta is equal to y over x. Simply what I'm going to do here is I'm just going to take the tangent of both sides. Okay, so the tangent of theta is the same thing as y over x. And the tangent of pi over 3, I hope you believe, is root 3. Tangent of pi over 3 is the square root of 3. We can now multiply both sides by x, and we'll have that y is equal to the square root of 3 times x. This is the answer. This is the equation of a line. It has a y-intercept at, well, the y-coordinate of the y-intercept will be 0, and the slope will be root 3. Let's say we have r is equal to 6 times the cosine of theta. So what we want to do here is we would still like to get one of these nice pieces here to show up. So it'd be nice if the r and the cosine were being multiplied together, because then I could replace it with x. But I'm not going to be able to do that by, let's say, dividing by cosine of theta. I'll have an r over cosine of theta. We don't want those kind of pieces. We need r squareds, and we need r cosines of thetas to show up. So to get an r squared to show up, I guess there would be two options you could do. You could either square both sides of this equation. Okay, that'd be good for the left-hand side, because we have an r squared. We could replace that with x squared plus y squared. But when we square the right-hand side, we'll get a cosine squared piece to show up. And there's really not much we could do with a cosine squared piece. I mean, I guess with the cosine squared piece, you could write that as, I guess, sine squared, like 1 minus sine squared. But I think that's not going to be super helpful for us. But what I think will be really helpful for us to do is to just multiply both sides by r. Because then I'll get an r cosine of theta piece to show up, and I'll also get that r squared. So in this case, instead of squaring both sides, it was nice to multiply both sides by r. So here we'll get r squared is equal to 6r times the cosine of theta. So we can replace this r squared now with an x squared plus y squared. And now this r cosine of theta, we can replace that with an x. So in some sense, we're actually finished. We have this all in terms of x's and y's. So we have this polar equation. This is its form in rectangular coordinates. However, I would say that this is not too satisfying of an answer because at least in its current form, it's not screaming at me what kind of shape it is. However, since we have an x squared piece and we have this y squared piece and we have another x piece here, what might be helpful for to do here is to try to complete the square. So let me go ahead and do that. I'm actually going to go ahead and subtract I'm going to subtract 6x from both sides. So I'm going to write this as x squared minus 6x. I'm going to leave ourselves a little bit of room. And then plus, we still have that y squared, and that's going to be equal to 0. Kind of section this piece off right here. Okay, so now what we want to do is we want to complete the square on this piece. So I want to know what number should I add here so this will factor to a perfect square. And hopefully we're familiar with how to do that. But what you do is you take the coefficient in front of x, so a negative 6. We're going to cut that in half and we're going to square it. So this will be the same thing as negative 3 squared, or this will just be 9. So I'm going to go ahead and add 9 inside the parentheses. But I can't just add 9 to the left-hand side. I also have to add it to the right-hand side to balance the equation. Okay. So now, this piece right here will factor to a x, looks like an x minus 3 squared plus a y squared will be equal to 9. So now after a little bit of massaging, hopefully this has kind of revealed to us what kind of shape it is. I hope we're familiar or recognize that this is actually, if we got rid of this minus 3, x squared plus y squared equals 9. That's a circle of radius 3. But if I subtract 3 from the x coordinate, that's going to shift the circle to the right 3 units. So this is a circle of radius 3 shifted to the right 3 units. Okay, 1, 2, 3. So we have our circle of radius 3. This isn't, I tried to be nice. It looks more like an ellipse, but it's a circle. This is a circle of radius 3. With center, let's see, its center will be at what? 3 and 0. Okay, let's say we have r is equal to a 1 all over a 1 plus, let's say, sine of theta. Go ahead and pause the video and give this one here a shot. Okay, let's do it. For this one here, I think what's kind of annoying is that there are fractions. Anytime I see fractions in an equation, I'm usually always going to want to clear them. So let's see if this helps us out. So let's multiply both sides by 1 plus sine of theta. And we'll get, at least on the right-hand side, we'll get a 1. And on the left-hand side, I'm going to go ahead and distribute this r in, which is going to be nice because, well, we'll get the r, which we'll have to think about how to deal with. But at least we're going to get a plus r sine of theta. And what's exciting about this is we can make this y sine of theta, an r times sine of theta. We could turn that into a y. So this is the same thing as r plus y is equal to 1. Okay, let's go ahead and solve for r here because we need to figure out how to get rid of that. So we have r is going to be equal to 1 minus y. This is a situation where it's not going to be nice for us to multiply both sides by r. It's going to make it r squared on the left-hand side, but then we have to deal with this extra r I'm going to get an r squared on the left-hand side, which we can deal with, but the r on the right-hand side will not be friendly to work with. So this is a great situation where I think instead of multiplying both sides by r, we're going to square both sides. So we'll get r squared is going to be equal to, we'll get a 1 minus y squared, and now this r squared can turn into an x squared plus y squared will equal to a 1 minus y quantity squared. Okay, so I mean, in a sense, we're finished. We've written this, this equation, this polar equation, in terms of rectangular coordinates. So this is a rectangular equation since there's only y's and x's. But in this situation, it's going to be really satisfying, I think, for us to try to simplify this a little bit. One thing that is screaming at me when I'm looking at this is if we are to expand the right-hand side, I'm going to get a negative y times a negative y. We're going to get a y squared. We'll have one on the right-hand side and on the left-hand side, and those will cancel. So this is at least screaming at me to do some canceling. So x squared plus y squared, and this is going to be the same thing when we FOIL this out. This will be a 1 minus a 2y. The negative 2y comes from the o and the I in FOIL. Negative y times negative y, we'll get a y squared. And sweet! We can subtract y squared from both sides. If we bring this up over here, we have that x squared is going to be equal to a 1 minus 2y. Or what we could do here is if we want to solve for y here, let's see, we could, how about we add 2y to both sides, and we subtract x squared from both sides. So this is if we divide both sides by 2 or multiply both sides by a half, this is going to say that y is equal to 1/2 times a 1 minus x squared. I think this is a great form to graph this in, but if you don't like the way this looks, you could say this is the same thing as 1/2 minus 1/2 x squared, or if you do plus the opposite, this is the same thing as negative 1/2 x squared plus 1/2. And I hope from here you recognize what this equation is. Let me move the screen a little bit. I hope we recognize that this is a frowny face parabola shifted up 1/2 units. So if we were to graph this, I think it might be even better to look at it in this form. In this form, this is the same thing as y would be equal to 1/2. If we factor this, that's a difference of squares, a 1 minus x times a 1 plus x. So this is a frowny face parabola. It has x-intercepts at x equals 1 and x equals negative 1. So I don't know. So here's 1. Here's negative 1. Okay, if here's 1, okay, here's 1/2. This is a parabola. A frowny face parabola has a y-intercept at 0, 1/2, and x-intercepts at negative 1 and 1. So I don't know. Even though this is a frowny face parabola, here I am. I'm smiling. This is great. Let's say we have the cosine of 2 theta is equal to 1. Go ahead and pause the video and see if you can convert this into rectangular coordinates. Okay, let's do it. You might be tempted to want to multiply both sides by r. So we get an r would be equal to the cosine of 2 theta. But if we had an r times the cosine of 2 theta, we can't replace this with x, because x is r times the cosine of theta, not r times the cosine of 2 theta. So we don't want to multiply both sides by r. So I think really what we're stuck with doing here, and what we kind of have to do here, is use our double angle formula. So there are a couple different versions of it, but I think the one that might be the nicest to work with is, this is equivalent to cosine squared of theta minus sine squared of theta will be equal to 1. Okay. So maybe we'll play around with doing a different version of it to see if we get the same thing. But this is the first one that comes to my mind to use. So now we can have. So now what can we do? What can we do now? Well, I think I think it might be nice for us to, I don't know, I would like an r cosine and an r sine to show up. So the only thing I can think to do here to get those to show up is multiply both sides by r squared. So that's what I'm going to do. Let's see what happens. Let's multiply both sides by r squared. Okay, let's see where this leads us. So we're going to get a r squared cosine squared of theta minus an r squared sine squared of theta will be equal to r squared. Okay. Well, what's nice is I can rewrite this as r times the cosine of theta quantity squared minus an r times a sine of theta quantity squared will be equal to an x squared. And from here, there's lots of replacements we can do. Not x squared, r squared. So r cosine of theta, that's the same thing as x. We have x squared minus, this is the same thing as y squared. And on the right-hand side, we're going to get an x squared plus y squared. Okay, well, what happens? Looks like we could subtract x squared from both sides. So we have negative y squared will be equal to y squared. How about we add y squared to both sides? So we'll get 0 will be equal to 2y squared. And I guess we could divide both sides by 0. Or sorry, divide both sides by 2. And we'll get that y squared is equal to 0. But if you square root both sides, y is just going to be equal to the plus or minus square root of 0, or y is just going to be 0. You could have almost noticed this almost from here, that the only solution to this equation would be plugging in y equals 0. But, you know, this is another way to get there. So this is the equation y equals 0. This is just describing the x-axis. So this is the equation y equals 0. Pretty much just the x-axis. So here we go. This is y equals 0. Okay, for fun, I guess, what would happen if we would have chose a different version of this double angle formula? What would have happened there? Sounds fun to play around with. I don't know. How about we make the replacement? How about I don't know. We could do. This is the same thing as 2 cosine squared of x minus 1 will be equal to 1. So let's see what this does here. Maybe this would have been easier to work with. Okay. Well, we could have added 1 to both sides. So we'll get what? 2 cosine squared of theta will just be equal to, what are we going to get? We're going to get, what, a 2? We could divide both sides by 2. So we could get cosine squared of theta will just be equal to 1. Okay, well, it would be nice to get r, have an r cosine of theta. So how about we multiply both sides by r squared? So we'll get what? This will be the same thing as an r times the cosine of theta quantity squared will be equal to x squared plus y squared. So this is the same thing as x squared would be equal to x squared plus y squared. Maybe it was easier to do it this way. Now we could subtract x squared from both sides. We'll just get that 0 equals y squared, and we're just going to get that y equals 0 again. So this way, probably this way was just a little bit quicker. Cool. So we just messed around with cosine of 2 theta being equal to 1. What about sine of 2 theta equaling 1? Give it a shot, pause the video, try to convert this into rectangular coordinates. Okay, well, we'd really like to have a sine of theta and a cosine of theta. So let's use the double angle formula for sine. I think that's 2 sine of theta cosine of theta will be equal to 1. Okay, what to do from here? Well, I have to kind of, in general, there's no, I would say, set a real easy way to go from polar coordinates to rectangular coordinates. Sometimes you have to try something. at least what I'm noticing here in this situation, it'd be nice if I had an r sine of theta and an r cosine of theta. So I think I want to multiply both sides of this equation with, 2 copies of r. So I want to multiply, we'll attempt it. What if we multiply both sides by r squared? Okay. So on the right-hand side, we'll have an r squared, which will be good news. Okay, on the left-hand side, well, there are 2 r's here. Oh, remember how sine is so friendly. Sine likes to share. Let's share the r. Let's give one of the r's to sine and one of them to cosine. So we'll have a 2, and then we'll get an r sine of theta, and we'll get a r cosine of theta. Okay. So here we'll get looks like we'll get a 2y and this will be an x, so we'll get a 2yx, and r squared is the same thing as x squared plus y squared. Okay. So now we have to take a look at this and see if we can really do anything with it. Sometimes we'll find that there's really not much we could do, but in this specific example here, I can smell some factoring. Here we have x squared plus y squared. We got like this 2yx. I'm going to move everything to one side. I think this is a quadratic. How about I make this x squared minus a 2? I have a yx. Or I could, how about 2yx plus y squared? And I think this actually factors nicely. Okay, I think this will factor to. I think this will factor to x minus y squared. Go ahead and FOIL this out. I think these are going to be equivalent. Okay, so looking here, we can actually see, you could square root both sides, but this is basically saying that y has to be the same thing as x. Y has to be equal to the same thing as x. So this is the equation. So this whole time, the sine of 2 theta equaling 1, this is just the line y equals x. This is just the line y equals x. So there we have it. That one was fun. Let's try something a little bit different. What if we had sine of 2 theta, not equaling 1, but how about sine of 2 theta equaling r? Let's play around with this one. What will this happen? What will happen here? Okay. Well, I still think that we're going to want to write this as a sine of theta, cosine of theta. Use the double angle formula for sine. Okay. And I still think we're going to want to get that copy of r on sine and cosine. So I still think we're going to want to square both sides. Or not square both sides, but multiply both sides by r squared. Okay, we're going to have to think about how to deal with this r cubed on the right-hand side. So we have r cubed. Okay, we're going to share the r, so we'll get a 2r sine of theta, and then a 2r sine of theta, r cosine of theta. So this will be the same thing as what? This will be 2yx will be equal to r cubed. So now what to do with r cubed? Well, this is a tough one. In this case, you could write it, I guess, as this is r squared times r. So I guess we could replace one of these. We could replace this r squared with an x squared plus y squared. Okay, that might be helpful. Let's see what that does. So we get a 2yx will be equal to, this will be an x squared plus y squared, but we still have this extra copy of r that we have to deal with. Okay, what to do from here? I still need to get this r to turn into x squareds and y squareds. Well, I don't want to multiply both sides by r. Sure, I'll get an r squared, which will be nice, but I'll have an extra r to deal with on the left-hand side. So I think this is a great time to square both sides. Let's square both sides. And so what we'll get here is this will be a 2yx. Keep it as quantity squared. You could distribute and make this a 4y squared x squared if you wanted to. But now when we square the right-hand side, we're going to get a x squared plus y squared, quantity squared, but we're also going to get that extra r squared here, which we can make a r x squared plus y squared. So here we're going to get a 2yx quantity squared, and that's going to be equal to, looks like an x squared plus y squared squared, and now I can make this an x squared plus y squared. Okay, let's move this up over here. So this will be the same thing. This will be the same thing as a 2xy quantity squared. And now I have a x squared plus y squared quantity squared, and then I just have a x squared plus y squared to the first power. Exponent rules allow us to add these together. So this is going to be an x squared plus y squared quantity cubed. Okay. So now the question is what to do with this thing? You know, there's nothing else we can do with this thing. I mean, you could expand this cubic on the right-hand side, but I don't think we're going to be able to somehow massage this. We're not going to be able to solve for y explicitly in terms of x. We're not going to be able to solve for x just in terms of y. It's going to be hard for us to recognize this as a shape maybe we've seen in the past. There's nothing else to do here. We're going to leave it just like this. And what I'll actually do here is, this is this polar equation in rectangular form. Its rectangular form is ugly. I'm going to plot these in Desmos for us in just a moment, but we're going to hold on to this one here. This is saying that sine of 2 theta equals r. This was equivalent to 2yx squared is equal to x squared plus y squared all cubed. Let's hold on to this one. Okay, we'll come back to it. We're going to plot that in Desmos. Sometimes when you're converting from polar to rectangular form, you'll be able to somehow do a massage to recognize what the shape is. Other times we won't be so lucky. Sometimes things in polar coordinates are really friendly, and in rectangular coordinates are very ugly. Let's do this one. How about r? How about r equaling 3 minus 3 sine of theta? Go ahead and pause the video and give this one here a shot. Okay, let's do it. Let's see. The only thing I could think to possibly do here, I mean, it would be nice to get an r squared. It'd also be nice to get an r times the sine of theta. I don't think we're going to want to square both sides right now because I'll get a sine squared. And again, I want like an r sine. I don't want to deal with the sine squared. So I think it might be nice. Sometimes you just have to try something. I'm going to try multiplying both sides by r. These are very puzzly type problems. Okay, so let's just multiply both sides by r and see what we get. So we'll get an r squared will be equal to, distributing in this r, we'll get a 3r minus a 3r sine of theta. So this r squared, sure, we can replace that with an x squared plus y squared. Okay, we still have this 3r. We have to figure out what to do with that r. And we also have, what is this? This is a minus, this will be a minus 3y. So we still need to figure out how to deal with this r right here. Okay, so let's isolate it. So here we'll have x squared plus y squared. Let's add 3y to both sides. And this will be equal to a 3r, so I just added 3y to both sides. And kind of similar to what we saw in the last example, I guess we could multiply both sides by r. Sure, we'll get an r squared here. But I'm still going to have the leftover r on the left-hand side to deal with. So the only thing I can think to do here is square both sides. Okay, so now we're going to get an x squared plus y squared plus 3y is equal to a 9r squared. And now we can make the replacement. This is the same thing as x squared plus y squared plus 3y. This is going to be equal to 9. R squared is the same thing as x squared plus y squared. And we're going to be in, x squared plus y squared, yep. And I was supposed to square both sides. Sorry, we're supposed to square both sides, so we should have another square on this side. Okay, and this is going to be another situation where, I mean, there's really not much we can do here. I mean, I'm seeing x squareds and y squareds on the right. You might be thinking, oh, maybe we could do some sort of factoring or completing a square. On the left-hand side, though, when you expand this, it's not going to be really friendly to work with. You're going to get things like x to the fourths, y to the fourth. You'll have x squareds times y squareds. You're going to have a lot of ugly pieces. I don't think we're going to be able to clean this up any further. This really is this polar equation's representation in rectangular coordinates. So we're actually going to plot this one also in Desmos, and let's see what it looks like. So it turns out that this equation has a pretty nice representation in polar coordinates. In rectangular coordinates, very ugly. Very ugly. Okay, so let's hold on to these and let's see what they look like in Desmos. We'll see you there. Let's go ahead and take a look at some of those polar equations that we kind of had a hard time representing nicely in rectangular coordinates. It turns out that some shapes are just more naturally described using polar coordinates than rectangular coordinates. So I think the first one we saw was r is equal to sine of 2. Now, when you're typing in polar coordinates in Desmos, you're going to use r and theta. So right now I just have r equals sine of 2. This is just a number. Whatever sine of 2 is, it's some sort of number. It looks like it's some number, I don't know, a little bit less than 1. And so this is saying that r is just equal to a constant, so it's just giving a circle. So if I just say like r equals 4, this is giving us a circle of radius 4, regardless of theta. You know, we're always out a radius of 4. And you can do 9 and so on and so forth. Here's our unit circle. Okay, but we had sine of 2. Now, if you want to do theta, you just type theta, and Desmos recognizes that. And look at this shape here. This is like a 4-leaf clover. This shape r equals 2 sine of 2 theta, yeah, 4-leaf clover. This shape, it's kind of rounded, it's kind of circle-y. I don't know if that's a good word to use. It's much more natural to describe this shape using polar coordinates than rectangular coordinates. Let's type in its version in rectangular coordinates, which we discovered. What was it? It was 2yx quantity squared, and that was equal to x squared plus y squared. And we had this, to the power of 3. And look, they're the same exact shape. They're the same exact shape. Pretty cool. Pretty cool. So again, in rectangular coordinates, ugly, ugly, ugly. In polar coordinates, beautiful. Describes this shape here beautifully. Okay, let's take a look at another one that we saw. All right, we also had r. We had r is equal to, we had 3 minus 3 times the sine of theta. Cool. All right, let's back this up. And here we have it. This is what 3 minus 3 sine of theta looks like. This has a the shape has a famous name because it looks a lot like a, well, we'll say a heart. It's called a carnoid, like heart, carnoid. Yeah, we'll say it looks a lot like a heart. Yeah, that's what I'll say. So we have the carnoid, and it has a, it's kind of circle-y, so it has a nice representation in polar coordinates. But if you try to describe this shape in rectangular coordinates, it has a very ugly rectangular coordinate form. X squared plus y squared plus 3y squared, okay, and that's equal to 9 times, let's see, what, x squared plus y squared. That's what we saw. And look, they're the same shape, they're the same. These are describing the same thing, just in 2 different coordinate systems. Rectangular coordinates, ugly, ugly way to describe this carnoid. In polar coordinates, it makes it very easy to describe this shape here. So sometimes working in polar coordinates describes shapes much more natural than rectangular coordinates. I think there's some other shapes. Maybe what's another cool one we can do? Another cool one is r squared is equal to sine of 2 theta, but Desmos won't let you, I don't think it'll let me plot. I don't think it'll let me plot r squared. I think I have to have r being equal to something in Desmos, so let's just try it. Let's see what it does. 2 theta. Yeah, it's giving me an error sign over here, but let's just take the square root of both sides. There we go. That's square rooting. That's what the same as doing to the power of 0.5. So look here, this is an infinity sign. So pretty cool. So r equals the square root of sine of 2 theta, or r squared equals sine of 2 theta. That gives us this cool infinity sign here. So maybe that'd be a fun exercise for you to do. Convert r squared equals sine of 2 theta into rectangular coordinates, and just maybe take a look at probably how ugly it looks. But here, the shape here is very naturally, very easily describable using polar coordinates. Pretty cool.